All right, here we go. Chapter 8, problem set 3. I normally like to do the odds so that you have the answers in the back of the book. But this is a good problem, and I wanted to make sure that we got this one done. So this is problem 38. It is an even. It says, in the figure, it's a potential energy versus position of a 0.2 kilogram particle. It gives us some reference points. UA is 9, UB is 12, UC is 20, and UD is 24. So it says that at this point right here, when x equals 5, it says the kinetic energy is 4 joules. And then it asks some questions like, what is the speed of the particle at 3.5 meters? Well, it says that there are no non-conservative forces. And what that means is that the total kinetic, or the total energy, is conserved. So that's the total energy. So we're going to call that total mechanical energy. And total mechanical energy is U plus K. So when x equals 5, it says the K is equal to 4. And it looks like the U here is equal to 12. So total energy is equal to 12 plus 4. And total mechanical energy must be equal to 16 joules. And what's nice is that's always going to be 16 for the rest of the problem. So that's going to enable us to kind of like navigate this problem fully. So now it wants to know, what is the speed when the particle is at 3.5? All right, so let's look at 3.5 over here. So we're at 3.5. We're at this point right here. I'm going to look over and I'm going to see that my potential energy is 9. So if we start from our general principle, that the total energy is equal to U plus K, and we know the total energy is 16. We look at this, and U is 9. We can see that the kinetic energy is equal to 7, and we know that kinetic energy is equal to 1/2 mv squared. Set those equal. 7 is equal to 1/2. The mass is 0.2. And speed there is equal to 8.37 meters per second. All right, the next one says, well, what is the speed when the position is 6.5? So 6.5 would be down here. So we're going to start with our general principle again. E is equal to U plus K. E is still 16, because there's no non-conservative forces, so the total energy is always 16 in this problem. If I look at the U here is 0. So K is equal to 16. It's equal to 1/2 mv squared. So 16, 1/2, 0.2 v squared, and V is equal to 12.6 meters per second. Now, it makes sense that this one is faster because it has less potential energy. There's a potential, less potential, more kinetic, more speed. Okay. The next one says, what is the position of the turning point on the right side and the left side? So what is the turning point? Well, a turning point occurs, TP for turning point occurs when the velocity is equal to 0, which means the kinetic energy is equal to 0, and the force is opposite the direction of motion. So what does that mean? So as the particle moves to the right here, from here, right, the potential energy goes up. Now, the thing is that if the total energy is equal to 16, and it's U plus K, what happens when the K is equal to 0? Well, 16 is equal to U plus 0, so the potential energy should be equal to 16 at the turning point. So if I look here, okay, this is 15, 16, 17, 18. So 16 would be right here. that means that right here is going to be a turning point. So how are we going to calculate that? And that also means that this is going to be a turning point also on the left side. So let's move over here. Same thing applies here. So this is the 16 joule line, and so that means that right here, that's going to be the turning point. So how do we find out where it is? Well, if you look at this graph, this is 7 here, this is 8 here, so it's somewhere between 7 and 8. Looks like it's close to 8. So let's see if we can find it. Well, at this turning point right here, okay, at that turning point right there, here's what we know. We know that, drop this down. That's what we're looking for, the turning point right there. Here's what I know. I know that the total energy is equal to U plus K. And this is 16, this is 16, and this is 0. So if I want to find out where U is equal to 16 here, okay, where that is, the first thing I'm going to know is the slope. So let's look at this line here, okay? So I know that the slope is going to be, if I do the change in the vertical, 24 minus 0 divided by 8 minus 7. So the slope is equal to 24. So if I'm going to find the equation of this line, say y is equal to mx plus b. So y is the potential energy, m is 24, x is the position, and b is 0 because 0 is where this one started. So I know this is my potential energy I need is 16, 24x. X is equal to 0.67. And so the turning point occurs when x is equal to, well, so it starts at 7, that's where I started my graph, so 7.67 meters. What about on the left side? Well, the left side turning point is going to be over here. So it looks like it's somewhere between 1 and 2, a little closer to 2, but we're going to use the same process here. So it's U plus K. We know this is 16, this must be 16 because that's 0, so U is 16. Let's get the slope of this one. So the slope of this one, if I look at these points here, so this is 20, this is 9, so I'm going to do 9 minus 20 on top. And it went from 1 to 3 on the bottom, so 3 minus 1. Slope is equal to negative 5.5. Let's put in y equals mx plus b. Y is equal to m is negative 5.5 x plus, and I started my graph here at 20. So I'm going to plug in. 16 is equal to negative 5.5 x plus 20. And I'm going to calculate that. Maybe, possibly. So I have 16 minus 20 divided by 5.5. So I got x is equal to 0.72. So the turning point is when x is equal to, well, I started at 1, so 1.72 meters. And that's consistent with what the graph shows. All right, let's move on. 39. 39, another problem similar to the last one. So we have a graph. All right, it says if the particle can reach 1, what is its speed when it gets there? So again, the energy is going to be conserved. So what we're going to start with is this down here. It says that the mass is 0.9. When the position is 4.5, the speed is 7. So what we're going to do is we're going to have to calculate the total energy. And before we do that, let's get the kinetic energy. So we know kinetic energy is equal to 1/2 mv squared. 1/2, the mass is 0.9, and the speed is 7 squared. So I'll put that in my handy dandy calculator, and this ends up being 22 joules. All right, so if I start the problem with our general principle that energy is equal to, the total energy is equal to U plus K, then my energy is equal to, we're talking about when X is 4.5, so right here. So we can see that UA is 15 plus 22. So the total energy is equal to 37 joules. Now I'm going to draw that in here. So this is 35, that's 40, so 37 is probably right here. So that's 37 right there. So that's the total. Now, what this means is that because the yellow line is underneath the red line of total energy, that when this is the potential, it still has a little bit of kinetic, so it totally can move to this position. Over here, though, we'll notice that it can't get farther to the right than this, because then the kinetic energy would be 0. So let's keep that in mind. So it wants to know, what is the speed when X is equal to 4.5? No, that's a lie. When X is equal to 1, sorry. Okay, well, E is equal to U plus K. So I know my total energy is 37. At 1, the potential energy is 35. So the kinetic is equal to 2. It's also equal to 1/2 mv squared. So 2 is equal to 1/2. The mass is 0.9. Speed squared. Speed is equal to 2.1 meters per second. The second thing it wants to know is, what is the magnitude and direction of the force on the particle as it begins to move to the left? Well, here's the definition we're going to need to know. The force on the particle is equal to the negative slope. So for these potential energy position functions, that's our definition. You can find the force if you can find the negative slope. So let's just calculate it directly. Okay, let's look at the slope of this line from here to here. So it's 15 minus 35. Divided by 4 minus 2. So 15 minus 35 is negative 20, divided by 2 is negative 10, but then it's already negative, so I have 10 newtons, and since it's positive, I know the force is to the right. The next section says, suppose instead the particle headed to the right, the positive x direction. If the particle can reach 7 meters, what is the speed? And if not, what is the turning point? And then what are the magnitude and direction of the force? So what we're going to notice here is that, as I stated in the last one, you can see that there's a turning point right here. Because the maximum, or the total energy here is 37. And so when it gets to right here, that's when the kinetic energy is going to be equal to 0. So when we're talking about a turning point, we know the total energy is 37, and the kinetic energy is 0, so the potential energy is equal to 37. So we know that that's the turning point, which means it can't get farther to the right than that, so it's never going to make it to 7. So let's calculate the turning point. First thing we need to know is the slope of this section. So if I look at my 2 points here, I can see that this is 45 minus 15. And that all happens between 5 and 6. So this is 30 divided by 1, so the slope is 30. If I write my y equals mx plus b, slope is 30. My intercept here is going to be 15. And I know my value is 37, so let's calculate that. So x equals 0.73, and so the turning point, I started counting at 5, so 5.73 meters. And that's consistent with, if I drop this down here, it's between 5 and 6, but closer to 6. So I'm okay with that. And again, the force, if the force is equal to the opposite, the negative slope, we already calculated the slope, which was cool. So the force is the negative slope, so negative 30 newtons, and because it's negative, it's to the left. All right, 45. 45 says a rope is used to pull a 3.57 kilogram block at a constant speed. That's going to be important. Okay, I'm going to write it down because it's important. It says constant speed. Um, 4.06 meters along the horizontal floor. The force on the block for the rope is 7.68 newtons, directed 15 degrees above the horizontal. What are the work done by the rope's force? All right. Well, before we start, I'm going to draw a quick force diagram for this because I think that's going to be useful. So the Earth pulls this down. That's the weight. We call that mg, and then the rope is pulling at a 15-degree angle. All right, now this rope is pulling to the right and up. Because the speed is constant, we know all the forces are balanced, which is important, which means that there's a frictional force here that balances out the horizontal component. And then there's a normal force here that is less than the weight because the up component and the normal force have to balance out the weight. So we can call this the rope force. This is the rope force in the y direction, and this is the rope force in the x direction. Here's our angle theta, and it's 15 degrees. Okay. All right, so let's try to find the work done by the rope force. Okay, that's the tension, that's the rope force. So the work done by the rope, well, it's got to be equal to the force by the rope times the distance that's parallel to that force. Well, what's interesting is that if my distance vector is to the right, that means that this Rx is going to be the parallel distance. So to calculate that, I need to get the rope in the x direction times the distance. Those would be parallel. To get that, I'm going to take the rope force, which is the tension, times the cosine of my angle, times the distance. So I have 7.68 times the cosine of 15 times the distance. And I think that's 30, let's check. 30 joules. All right, the next one says, what is the increase? What is the increase in the thermal energy? Okay, what is the increase in the thermal energy? Well, so the change in the thermal energy, which we call the work done by friction, okay? How are we going to figure that one out? Well, the thing is we have to reason this one out first, because what does it say about the speed? The speed is constant. Since there's no change in kinetic energy, that means that all that work done by the rope had to go somewhere, and where it goes is into increasing the thermal energy. So that means that our increase in thermal energy is also 30 joules. That is an interesting idea. So whatever work you did all went into thermal energy, which is then released to the surroundings, and we end up with the same amount. So the last question here is, what is the coefficient of kinetic friction? So what's nice is that if you want to calculate the work done by friction, well, you need to know the frictional force times the slide distance. All right, well, let's bring this up here. The work done by friction is equal to the frictional force times the slide distance. What do we know about the frictional force? It's equal to coefficient of kinetic friction times the normal force. But talk to me about the normal force here, right? If I look at this equation here, something that I notice is that because the forces are balanced, because there's no acceleration, mg is equal to n plus the r in the y direction. So the normal force is equal to the weight mg minus r sine theta. So if I go to calculate this, work done by friction is equal to coefficient of kinetic friction times the normal, which is mg minus r sine theta times the distance. And so I know all these pieces. So this is 30. Coefficient of kinetic friction. mg is equal to, well, we got the mass right there, 3.57 times 10 minus 7.68 times the sine of 15, all times the distance, which is 4.06. Sorry for the squeeziness. Coefficient of kinetic friction is equal to 0.22. All right, 53. 53 says a 3.5 kilogram block is accelerated from rest by a spring compressed 600 with a spring constant of 640 newtons per meter. The block leaves the spring at the spring's relaxed length and then travels over a horizontal floor with a coefficient of kinetic friction UK is equal to 0.25. The friction stops the block in a distance of 7.8 meters. What are the increase in thermal energy of the block floor system? All right, so that's the first thing I'm going to do. So the increase in thermal energy, we talked about that in the last problem. So the increase in thermal energy, which we call the work done by friction, is equal to the frictional force times the slide distance. Luckily this time, this block, as it slides, you only have three forces. You got the mg, you got the n, and you got the friction. So n and mg are equal this time. So if this is equal to mu n d, we see that n and mg are the same. I think we have all this. So kinetic friction is 0.25. The mass is 3.5. G is 10, and the slide distance is 7.8. Calculate that real quick. And I got 68.25 joules. So that is the increase in thermal energy of the block floor system. What is the maximum kinetic energy of the block? I think we're going to have to reason this one out also. What is the maximum kinetic energy? If we think about the way this looks, when this started, if we think about, this is when it was in contact with the spring, this is when it left the spring, and this is when it came to a stop, we would see that this one's all thermal energy. This one was all elastic energy, and this one is all kinetic energy. So it turns out that all three of these have the same value. The thermal energy that was lost to the surroundings was equal to the maximum kinetic energy, which is right when it left the spring, which was equal to the total elastic energy that was stored there. So the question is, what was your kinetic energy max? And it had to be the same that was all lost, 68.25 joules. And then the next part says, what was the original compression distance of the spring? Well, what's nice is, since we know what the original elastic energy was, elastic energy is equal to 1/2 little k x squared. We know this was 68.25 joules of energy. 1/2, the spring constant was 640. And then you can solve for x directly, and I got 0.46 meters. 55, last one. 55 says, a block of mass 2.5 kilograms slides head on into a spring of spring constant 320 newtons per meter. The coefficient of kinetic friction between the block and the floor is 0.25, while the block is in contact with the spring and being brought to rest. What are the work done by the spring force, the increase in the thermal energy, and what is the block's speed just as it reaches the spring? No problem. So it's moving on its way in. So what's interesting about this problem is that we can use the conservation of energy concept to get this thing started. We can say that the initial energy has to be equal to the final energy. So initially it was just moving, all kinetic energy, but it slides on a rough surface and hits the spring. So we're generating some elastic potential energy, and because it's sliding on a rough surface, we're losing some of our energy to the thermal energy, which is the work done by friction. So here's our basic energy statement here. Now, the question is how much work was done by friction and how much work was done by the spring. So the piece of information that's necessary here is that it says when it hits, it compresses the spring. So this spring gets compressed 0.075 meters. It says it compresses it it says it compresses 7.5 centimeters, so it's 0.075 meters. So what this is going to allow us to do is it's going to allow us to calculate the spring energy. So if I want to calculate the spring energy, I'm going to use 1/2, sorry, a little muscle spasm there, 1/2 k x squared. The k, it tells us, is 320. It compressed at 0.075. Don't forget to square it. And 0.9 joules. So that's how much energy is stored in the spring. Now, the question actually asks, what is the work done by the spring? And in this case, this is also equal to the work done by the spring, because the work done is equal to the potential energy. And so in this case, we end up with the same number, but it asks what's the work done by the spring. So that's fine. How are we going to get the thermal energy generated? Well, the thermal energy generated is the work done by friction. It's equal to the frictional force times the slide distance. So the frictional force is mu mg/d, and we know that because it's on a flat surface. So I'm okay with that. The coefficient of friction is 0.25. The mass is 2.5. G is still 10. And now, what's the slide distance? Well, it slid when it was compressing the spring. So it turns out that the slide distance is 0.075 meters. And I got 0.47 joules. So I know that all the kinetic went to the work done by the spring, which was 0.9, and the work thermal energy generated, which was 0.47. Therefore, the kinetic energy that it was that it had before it hit was 1.37 joules. Now, I also know that kinetic energy is equal to 1/2 mv squared. So if I set these two things equal, again, mass is 2.5, I can find the speed. Speed was, oh, look at that, 1 meter per second. That wraps up Chapter 8, problem set 3.